Hello everyone, welcome to my presentation. My name is Haifeng Zhang from Australian Bureau of Meteorology. Today I'm going to be talking about a piece of work that we did a few months ago, which is the validation of Bureau's Himawari-8 SST retrievals using ISA measurements. Now before we get started, allow me to acknowledge my co-authors, Helen Beggs, Christopher Griffin, and Pallavi Gavkar. Helen and Pallavi should be sitting in the room as we speak, and I'll be joining you remotely from Melbourne, Australia. So in this talk, I'll briefly touch on the background and the motivation for this study. After that, I'll move on to the datasets, quality control, and methods used in this study. And then I'll present some results before I draw some conclusions and talk about the future topics, a few of them that we have in mind. And this presentation is based on this publication, and it was a paper published in Remote Sensing. The link is here. Feel free to click on it if you can, but reach out to me for a copy if you're interested. Now, background and motivation. The Bureau is one of the several agencies in the world that are currently operationally producing Himawari-8 SST products, in addition to NOAA or JAXA. This product is very important in Australia in terms of, for example, data simulation into the regional ocean models that we use at the Bureau. Now, there are several publications on the validation of NOAA or JAXA SST product, but there are few on the Bureau's product. Therefore, we think this work is essential, especially that the Himawari-9 SST product at the Bureau is going to be operational next year. This gives us strong motivation to evaluate the current product, to see where we are doing well, where we are not doing so well. And another motivation for this study is to evaluate the quality of the reprocessed shearborne ISA measurements, which are often considered as the optimal option for satellite validation. Now let's move on to the datasets, quality control, and methods used in this study. Now I'm going to spend a few minutes on this slide as it contains quite a bit of information, which is very important to understand our results. So first, the satellite product that is to be validated is the IMOS FV02 version Himawari-8 skin SST Level 2 product. Time spans for 5 years from 2016 to 2020. All the other data sets are from Research Vessel Investigator, including the ISA Skin SST. Now the ISA SST measures skin SST at the same depth as the infrared radiometer on board the satellite. So it's going to be the basic ground truth data set in this study. Another SST dataset is the Seabird SBE38 depth SST, typically at 7 to 10 meters. This SST dataset is not directly used in the satellite validation, but it's only used to visually QC ISA measurements. I'm going to come back to this very soon. And a series of environmental conditions were obtained concurrently from the same ship: wind speed, air temperature, humidity, and shortwave radiation, etc. Before we get into the data analysis and get any useful results, quality control on these products is of fundamental importance. And we are going, let's go through several major QC steps here. First, for the satellite measurements, we don't want any cloud contaminated pixels, so we keep only the quality level 5 pixels. The probability of clear variable is set to 1, the highest, and every pixel is bias corrected for future analysis. For ISA measurements, we keep only those with a total uncertainty smaller than 0.2K. For all the other measurements, we are going to trust our automatic QC scheme employed in the IMOS data processing system here at the Bureau. Now, after QC, it's time to create the matchup database. Temporal window is set to 5 minutes, spatial window 5 kilometers. In this study, only the best pair is returned. Now, before we get our final matchup database, one more step, QC step here, is to visually quality control the ISA measurements. Now, we are doing this is because we know that for some voyages, the ISA instrument was not performing very well, and the data can be problematic. So we decided to visually quality control the ISA measurements by looking at every voyage. We are doing this by comparing ISA with the SPE38 depth SST here, and only under well-mixed nighttime conditions. So theoretically, under such conditions, the only difference between ISA and SPE38 SST should be the cool skin effect. On average, the nighttime cool skin effect can be anywhere between 0.1 to 0.4K perhaps. And we decide that if the temperature difference between these two is higher than, say, for 3 times the average nighttime cool skin effect amplitude, we are going to be like, okay, we cannot trust this voyage, and it has to be deleted, including the daytime measurements. With this QC step, we have identified 5 voyages within the 5 years that the data is not trustworthy, and they are not included in the following analysis. And finally, we have our final best quality matchup database here. As you can see from this plot, most of the measurements are made along the Australian coast, and the color bar indicates the ISA SST. So this matchup database is relatively large, with 31,000 matchups in total, including 16,000 during daytime and 15 during nighttime. And now it's time to look at some of the results. And in this section, I'm going to introduce a diurnal variation case study first, then show you some statistics that you might be most interested into. And then we're going to look at some of the plots showing how the satellite product performs under different environmental conditions. So a strong diurnal variation event happened on October the 12th, 2016, near the northeast Australian coast. And this plot is showing all 3 SST datasets during this 24-hour period. And blue is satellite, red ISA, and green is depth SST. Now, as expected, there's hardly any diurnal variation in the green line at that depth. And also we can easily see that the blue dots are following pretty closely with the red dots during this whole period. That means the satellite is actually picking up the diurnal variation signal pretty good. So after this case study, this product has left us with a pretty good first impression, can be trustworthy and sensitive to the diurnal variation, to the skin SST signals. Now here are some fundamental statistics for the daytime and nighttime temperature differences. The temperature difference delta T here is defined as satellite SST minus ISA SST. So in this plot, the X is delta T centered at 0K, and the Y-axis is the population, the number of collocations within each small beam of the delta T. Blue is nighttime and orange is daytime. We can easily see that the blue measurements are clustered close to 0K in the middle, and the distribution of the daytime measurements, delta T's, are wider with thicker tails on both ends. Now, number-wise, the daytime mean bias here is minus 0.12K, standard deviation of 0.47K, and the nighttime, the bias is much closer to 0, and the standard deviation is also smaller at 0.37K. Now, after the case study and the overall statistics, we want to see how this satellite product behaves under different environmental conditions. Now, we are going to show a few here as examples. The first one is wind speed. Daytime and nighttime are separately analyzed here. To the left is the daytime, a plot of daytime. X is wind speed and Y-axis is delta T. The gray bar here presents the number of collocations, and the blue line here is the delta T. One thing that really stands out in this plot is that there is a cold bias under almost all the wind speed conditions. However, on the right-hand side, for the nighttime, the blue line is closer to 0K at almost under all the wind speed conditions. Next is the dependence of the delta T on local solar time, and the left plot shows. In the left plot, the X is local solar time for 24 hours, and the Y is again delta T. And we can see that during the night time, which is before 5 a.m. or after 8 p.m. local time, the delta T is really small. It's very close to 0. And I want to point out here that during the dawn or dusk times, the match-up collocations are much fewer. That is because of the sun glittering effect in the satellite retrievals. We don't have a lot of satellite measurements available at these two times. But during the daytime, a cold bias is really obvious for almost all the hours, especially around the midday, like 12 p.m. local time. And very naturally, we want to know that if this is in any way related to the shortwave radiation, which is the largest during the local noon time, and we got this right plot here. I mean, it's hard to tell if there is any distinguishable dependence or if there's any pattern or trend in the blue line here. We do observe a declining trend when the shortwave radiation is larger than 1000, but with only a few measurements, it's hard to draw any conclusions here. One more environmental condition to show here, the relative humidity dependence. Now in the left panel, we do see that as the relative humidity gets larger from 30% to 70%, the cold bias does seem to get closer to 0. I mean, that's for the daytime, but during the nighttime on the right panel, there's no such trend at all, and all the delta T values are pretty close to 0 under all the relative humidity conditions. A final result I want to show here is a direct comparison with JAXA product, which was validated in a previous paper by Minglan Yang in 2020. I hope Minglan is also in the audience, so we can have a discussion after this. But in Yang 2020, they were using the same ISA SST scheme, SST, and SB38 SST datasets to validate the JAXA level 2 products. And they have performed a case study using just one voyage in 2016 to make the comparison as direct as possible. We have also performed the same case study using for the same voyage, and the results are shown here in this table. So basically, all the numbers in our study are larger. For example, we have a much larger matchup database in both daytime and nighttime. Mean biases are larger, the code biases, especially for the nighttime, which is really surprising to us. And also we have standard deviation larger than Yang 2020. And we have thought about it, and we think a few reasons might be responsible for the statistical inconsistency here. For example, in Yang 2020, they have adopted a much stricter quality control, which is not employed in our study. So that is all pixels within a 7x7 window centered around a target QL5 satellite pixel should all be of QL5. Another reason could be that there are some unexpected code biases during the nighttime in the Bureau's products. We were expecting some code bias during the daytime, but not the nighttime. And another reason that could be a major one is the spatial windows are different in these two studies. We used a 5-kilometer threshold, but Yang 2020 used a 0.02 degree window. And then there are other causes, minor causes perhaps, such as different algorithms and channels like radiative transfer model versions and WP inputs, etc. But we don't know how important these factors can be. Now it's time to draw some conclusions here. After this study, we believe that the Bureau IMOS FV02 Himawari-8 level 2 product have A, high sensitivity to the skin temperature variation, B, it has overall very good quality, but we do see a cold bias during the daytime under almost all the environmental conditions, but in the nighttime, the data is consistently more stable. And once again, we have confirmed that the reprocessed ISA measurements can be a very reliable fiducial source of ground truth for satellite infrared SST validations. In the future, there are a few topics in mind. For example, we want to dig deeper into the daytime code bias and the unusually many code outliers during the nighttime in year 2016 was really a surprise to us, and we want to look further into that. And also with the operational Himawari-9 data coming in June 2024, we hope to validate that product as well using similar ISA measurements. That is the end of my presentation. Thank you very much for listening, and I'm happy to take any questions. Thanks.